Hello, my name is Nicholas Bramhall, and this is my lab report for Lab 4. Alright, first up, the introduction. So, the point of this lab was to simulate a real-life spring and use that simulation to demonstrate how the spring moves and how that energy changes as it's moving. Now, for this lab, the system was a spring, the block, and the earth, and this was so that we could use potential gravity and the spring potential energy. Uh, and the surroundings was just basically everything else. Now, the methodology is it's quite simply we record a video of a spring moving, we put it in Tracker, we extrapolate the data, and then using that data, we can import that data into our code model, and we can put them side by side and like kind of see the graphs and see how they're correlating to each other. And this would confirm the energy data that we're extrapolating from the simulation and that it is applicable in the situation. Now, these are the formulas we're using. So the FNet velocity and position update formulas that we can see right here, these three right here, this is just like make sure that the spring is moving in the simulation, and it would be used to update the position for the spring and the potential um, energy and the gravity potential energy. And then using that, we can get the kinetic energy from the velocity as well. Now, the model. So we can see at the top we have the initial conditions in terms of the position, the mass, and then the relaxed length of the spring right here. And then going from there, we can then calculate the L hat, and then the formulas for the energy, which are then slotted into the initial energies over here on the right. Moving from there, we calculate the gravity and the spring forces, and we add them together for the FNet, which is then used right here to calculate the velocity and then position. Using position, we once again update the stretch length of the spring, the direction of that, and then the delta L, which is calculated as S. And then from there, we can calculate the energy chain, the new energy, and then we do the new energy minus the initial, which was assigned up here. And then finally, this energy alone is just all of it added together. Moving on from here, we have the actual results of the lab. On the left, we have the graphs. And you can see here that the graphs are oscillating right here, where as the delta U spring is increasing positively, meaning it's going downwards, the gravity is actually getting lower. And then if you're going, and as the potential energy for gravity is increasing, the spring is decreasing into the negative. Its magnitude is still increasing correspondingly, but it's now negative because it's now increasing in a different direction. More importantly, you can see that energy is held constant, showing that they're all added up correctly. And then we can see here too that uh, that delta K is 0 where they meet, and that makes sense because that's where the K is actually at its greatest, where velocity is at its max when it's in the equilibrium state. However, at that point, it's not changing because it's at its max, and that's why it switches over from negative to positive or positive to negative. Over here on the X, we can see that the model is consistent and it's matching up very similar to the experiment until we get later, which is most likely attributed to drag not being in the model, but it is in real life. And similarly here, we can see that the further along we get, the less it actually reaches that peak, once again, most likely the lab. You can see here the kind of like the movement of the spring, and here we also have it kind of moving in that diagonal direction as well. So, what does it mean? Well, for the model system, we can see that the energy principle is satisfied from the fact that delta K is always at 0, meaning energy is conserved, and that two potential energy springs are opposite because as one is increasing, the other one is increasing in the opposite direction. And we also talked about delta K already. And we can see here too that these are some estimated oscillation periods from the tracker data. And we can see here as it's going on, the general trend is that it's decreasing, which makes sense due to drag being a resisting force, increasing the amount of time needed to reach that time period for oscillation. But overall, they are, when you take the average, the X is a little bit bigger due to the fact that it's fighting against less amount of forces. So that also makes sense. Now, when we're talking about sources of error, the only real ones would be the lack of accounting and drag in the model, and then also inaccurate point placing in the tracker. Those are the two major ones because the data is pretty consistent with what the math would be. So we can have confidence in that. And that's about it. Thank you for taking the time to watch this.